Alright, so in this video I'm going to talk through the concept of mechanical energy. So first of all, what is it? So mechanical energy is the sum of the potential energy and the kinetic energy of an object. So it's those two things combined which make mechanical energy. So first of all, what's kinetic energy? So kinetic energy is the movement energy of an object, and it has this equation to calculate it. So kinetic energy is half times the mass times the velocity squared of the object. Except we don't really need the velocity, we can just get away with using the speed. And the reason we can do that is because kinetic energy is a scalar quantity. So it has magnitude but not direction. So because kinetic energy is a scalar, we only need the scalar form of speed to calculate it. So we just put speed in there, not necessarily velocity. Potential energy is a form of stored energy. So when you lift an object off the ground, you're giving it potential energy. So when you release it, essentially it will fall back to the ground, so it will gain kinetic energy, so that potential energy gets released. And you can calculate the potential energy change of an object by knowing its mass, the gravitational field strength, or gravitational acceleration, and the change in height. So the greater the change in height, the more potential energy you give it. So if we want to go about changing the mechanical energy of an object, either to increase its potential energy or to increase its kinetic energy, we need to do work on that object. And work done is force times the distance moved in the direction of that force. So you have to be very careful in questions that you actually look at the force component in the direction of movement. So be a little bit careful with these. But that's the work done equation. So let's have a look at an example question. So we've got a 25 gram bullet and it's fired at a 3 centimeter thick wooden barrier. It's starting off at 200 meters per second and the resistive force from the barrier is 5,000 newtons. Okay. So first of all, let's calculate the work the barrier can do on the bullet. So work done is the force times the distance. So the resistive force is 5,000 newtons and the distance was 3 centimeters, so that's 0.03 meters, and that gives you a work done of 150 joules. Now, the kinetic energy to start with before it's encountered the post is calculated using this equation here. So you're going to have the mass of the bullet in kilograms times by 200 squared divided by 2. And that kinetic energy comes out at 500 joules. So if we compare these two numbers, we can see that the work done by the barrier is in no way going to overcome all of the kinetic energy of the bullet. So all it's going to do is cause it to slow down. It's not going to be able to cause it to stop. So if we want to calculate the final velocity of the bullet, first of all we need to think about the change in kinetic energy. So that's going to be the total before minus the difference equals 350 joules. And then if we want to calculate what that speed is, we can essentially rearrange the kinetic energy equation into this form here. So it's going to be the square root of 2 times 350 divided by the mass of your bullet. And then that will leave you with a velocity of 167 meters per second. So the barrier is going to cause the bullet to slow down, but it's not going to cause it to stop, and it's going to slow it down to a speed of 167 meters per second. Alright, so there is that nice and typed out in case you couldn't read anything I was doing, but let's move on to look at power. So those of you who are fans of cars and maybe like watch Top Gear or anything like that, you've probably heard of them talking about horsepower. And generally when you watch those programs, you go, more powerful cars equal more expensive and better, faster. So why is that? So the power developed by an engine is the force it's supplying and multiplied by the velocity at that current time. So if an engine develops a force F and it's traveling at a velocity v, you can calculate the amount of power that the engine is generating. So if you have a higher power engine, so you have more horsepower, that means when you're at a higher velocity, you can still develop a large force to accelerate. So even when you're at very high speeds, which most cars would have a very low force by that point because they were limited by their power, but at the high speed, if you have large power, then you still have a large force and you can still keep accelerating. And those of you who want to know, 1 horsepower is 746 watts or 746 joules per second. And just as a historical side note, if you want to know why it's called horsepower, essentially the first steam engines were actually used to replace horses in terms of lifting things. And so the initial engines could lift about as much as 2 horses, so they decided to rate their power in horses. So not at all relevant for the course, but a fun fact nonetheless. Let's have an example of putting that all to good use. So let's look at this question here. So we've got a car of mass 900 kilos. It's down a slope angled at 2 degrees to the horizontal. So let's, as always, do a sketch. So we've got 2 degrees in there. We've got mass of 900. So that's going to be acting that way. Looks a bit like a 4. That's 900 G. And outputs a power, so power of 45 kilowatts, or so that's going to be 4.5 times 10 to the 4 watts. And the resistive force is 1700. Calculate the maximum speed. So let's let the driving force be equal to D, and let's have a look at how this is going to work. So when it's at maximum speed, the acceleration is going to be 0, which means the resultant force is going to be 0. So the engine is driving with a force of this. It's also got the weight force acting down the slope with this amount, but it's got a resistive force of 1700. But at maximum speed, we know that's going to be equal to 0 because there'll be no resultant force at maximum speed. So if we rearrange that, we can get an expression for the driving force, which would be 1392 newtons. Now, power is force times velocity. So if we want to calculate what the velocity is at that point, we need the power divided by the force, which in this case is D. So we've got our 4.5 times 10 to the 4, and we divided by 1392, and we end up with a maximum speed of 32.3 meters per second. Okay, so that's the worked example. Again, you couldn't quite read anything I was writing. There it is, nice and typed out, and that's the content I'm going to be looking at today. So that's us done with mechanical energy and with power.